Okay, Arya. This is, forgot this one. This is the activity on page 20, right? Activity 3 on page 20. It says determine whether the function is continuous or not at the indicated point. Is continuous or not at the indicated point. In the event the function has a removable discontinuity, extend the function. When we have a removable discontinuity, we should extend the function, the definition of the function, so that the new function is continuous at the given point, right? Now, let's start in part A. Okay, part A says it's f of x equal 1 plus x squared over x squared, and we should study the differentiability when x equals 0. All right, first, is it defined at x equals 0? We have x squared in the denominator. This means x squared should not equal to 0. This means that x should not equal 0. So what is the domain of the function f? Domain of the function f is all set R without the point 0, because 0 makes the denominator 0. If x equals 0, x squared equals 0, so the denominator will be 0, and the function will be, in this case, undefined. This means, for sure, directly we can say that f is not continuous at x equals 0. At x equals 0, we have discontinuity. Why? Because f is not defined there, right? It's not defined there. Directly we can consider that. But he wants us to see if it is removable or not. If it is removable, we have to extend the definition. We have to make a new definition in order to make the function continuous at the given point. Is it removable? Let's see. To know if it is removable or not, we find the limit of f of x at that x tends to 0. We get what? It's a limit of 1 plus x squared over x squared as x tends to 0. Substituting 0, we get 1 plus 0 over 0, which is 1 over 0. That gives me plus infinity. Infinity means it's not removable. Not removable. So, end of this part. Not removable. We shouldn't do anything here. It's enough to tell him not removable, because the limit is infinity, tends to infinity, and in this case, since f is not defined at x equals 0, this means f is not continuous at x equals 0. Okay? This is part A. Let's go to part B and see what's the difference between them. Part B. Part B says f of x equal x squared minus 2x divided by 0, divided by x, only x, divided by x, and where x equals 0. We need to study the continuity when x equals 0. First, what is the domain of definition here? Since x is in the denominator, this means x shouldn't be equal to 0. So domain of definition is all sub R without this 0 in the denominator, right? So directly I can tell him that f is not continuous also. Is not continuous at x equals 0. Also because f is not defined. Is not defined. Where at x equals 0, it's out of my domain. It's out of the domain of definition. This means it's not continuous. That's not enough, because the question wants me to check whether it is removable discontinuity or not. Let's see if it is removable discontinuity. Okay. How to know that? Limit of f of x as x tends to 0 is equal to what? Is equal to the limit of x squared minus 2x over x when x tends to 0. And this equals to limit as x tends to 0 of x into x minus 2 by factorizing the numerator, right? Because we cannot substitute 0 anyway. If we substitute 0 here, it will be 0 in the denominator and 0 in the numerator as well. So we don't substitute, okay? So what we do is because 0 over 0 is not defined form, we change the form by factorizing, and I did factorize. We simplify, we cancel the 0. We got the limit of x minus 2 as x tends to 0, and this is equal to minus 2 when we replace the 0 instead of x. Since it's not infinity, then the discontinuity here is a removable discontinuity. So f has removable discontinuity, where at x equals 0, it is discontinuous, but it is removable, not as the first part was not removable because the limit gives us minus infinity, and here, the limit gives us infinity there, and here gives us minus 2. Now, how to extend this? If we say f of 0 equal minus 2, we have to extend the domain for having f of 0 equal minus 2, not having f of 0 equal 0 over 0, which is undefined. In this case, if you want, we can write a new f of x, which is the main f of x that was given by the book, but we can tell him where, in this case, x should not equal 0, and x minus 2 if x equals 0. So now we did extend the definition of f of x, and that's it.